Hello guys, today we continue discussion of diffraction and we introduce such a optical instrument as diffraction grating. So diffraction grating, as you can see on this image, is a system of periodic uh, slits where like on which of them um, diffraction of incident plane monochromatic light or mixture of different monochromatic uh, lights can diffract. So as a result of such diffraction on a system of periodic grating, we get different orders of diffraction maximum. So here we see this central one is the uh, zero order maximum, and these two are first order maximum at m equal 1 and m equal -1. They are symmetric with respect to the zero order maximum at angle theta equals 0. And obviously we will have higher orders maximum, like second, third, which are just not revealed here on these schematics. So as a result, we get system of maxima. This is the distribution of light intensity of this plane light wave, which diffracted over this diffraction grating. And we have very distinct, like sharp peaks at different angle position with respect to the main central or zero order maximum. So if we look closer to the structure of diffraction grating and interaction of plane wave with this grating, we see that this distance d, distance between two neighboring slits in the diffraction grating, is called the period of diffraction grating and defines actually its resolution, how well it will split, for instance, visible light in two different into the spectrum, taking into account that for each wavelength we have very narrow diffraction maximum. So for other wavelengths it will be another narrow diffraction maximum next to it, and so on. So we will split the visible light into a spectrum, and if this distance d, the period of diffraction grating, is small, then we will be able to see the fine structure of incident light, like spectral fine structure of incident light, and learn a lot about the source of this light from, for instance, from chemical composition, because that provides us information about the atoms which are involved, like excited atoms which are sources of light in the object which emits this light, and detailed analysis of the spectrum of emitted light will provide us the chemical composition of this medium. So the condition for the maximum of diffraction of a diffracting grating is defined as follows: d, the diffracting, the period of diffracting grating, times sinus theta, angular position of the maximum, is equal to m lambda, where m is changing like from 1 to and so on. So now, as you already may understand, that this diffracting grating with very small periods d are widely used in different optical instruments, specifically spectrophotometers. So there are two options. Either light is going through the diffraction grating, as shown on this slide, or there is option that light is reflected from diffracting grating. So it depends on the material from which we make these diffracting gratings. So let's say if it's some glass substrate where this some pattern of diffracting grating is scratched on the surface, then light can go through such diffracting grating. However, most commonly used and the highest quality are metal diffracting grating, when there are trenches made on the surface of metal, and then light is reflected from the surface of this metal diffracting grating. And with such approach, it is possible to obtain the highest spectral resolution. The main application, if we generalize, the main application of diffracting gratings is to determine the wavelengths on incident light. So either we deal with, if we deal with monochromatic light, then we have just one task to determine the wavelengths of incident monochromatic light, because we can apply these conditions for maximum of diffraction pattern of this diffracting grating at given wavelengths. Or if we have some white light and in any way we kind of, by applying this, shining this white light on the surface of diffracting grating, we split it in the spectrum, and then we can identify wavelengths of each components which form this white light. And also our analysis leads us to this generalized task of determining unknown wavelengths of incident light. So with this, we move to another slide, and here we will show very simple way how we can use the simple diffracting grating in form of CD and DVD discs to determine wavelengths of two lasers. So we have red laser and blue laser. So let's assume that these wavelengths are not known. Actually, that's true, even if they are specified in the technical information from the manufacturer. There is quite a large standard deviation for provided wavelengths, because this type of lasers are not so precise in terms of output wavelengths. So for our experiment, we will need CD and DVD discs, two lasers, as I mentioned, and also we use just some ruler. So obviously that this experiment is has some demonstrational purpose. We are not trying to make it very accurate. However, we will clearly show you the concept and the sequence of steps which are required to determine with some, like, let's say, estimate with some level of accuracy the wavelengths of these two uh, monochromatic light sources, red and blue. So if we look closer to the structure of compact disc DVD discs, we will see that there are traces of pitches on the surface of this discs, and for CD disc we have the distance between the two neighboring traces, which is 1.6 micrometers. So it's repeatedly placed traces 1.6 micrometers next to each. And for DVD disc, we have more packed traces. So they are placed with respect to each other at the distance of 0.74 micrometers, or in other words, 740 nanometers. So taking this periodic structure into account, it's actually this system can work as a diffracting grating working in the reflected light, because we know that this surface of the CD and DVD discs are quite reflective, so we can shine light on the surface and reflect it to some screen. So our experimental, simple and very straightforward demonstrational experimental setup will look like this. We managed to fix CD. Initially, we start with CD disk next to some screen, like some flat surface, where we will project the diffraction of incident laser light on this screen. So the distance between the disk and the screen was set to 35 centimeters, or since we operate in meters, then we will have 0.35 meter. So then we align monochromatic light source, our first laser, red laser, and that way that the incident beam is reflected from the surface of the CD disk. Then we get reflection, like we have diffraction of incident beam, and this diffracted light is reflected from the surface of the CD disk, and we see the projection of this diffraction pattern on our screen. So here we see the zero order diffraction maxima and two first order diffraction maxima. So our goal is to determine the distance between zero and first diffraction maxima, and taking into account this demonstrational nature of the experiment, Obviously, there is some deviation in the alignment of incident beam and diffracted light. So in order to reduce the inaccuracy, what we need to do, we need to measure this distance between two neighboring like diffraction, first order diffraction maxima, and then divided by 2, let's say, and then this distance between the first and zero order diffraction maxima we will denote as x. Then here distance will be small l equal to 2 times x. So measuring the distance between two diffraction first order diffraction maximum and then divided it by 2 will allow us to reduce the errors in our experiments, and in this case the distance like x between 0 and first order diffraction maximum was, so the distance between first order and zero order maximum was measured to be 0.16 meter. And we keep in mind that this distance between the CD disk and the screen is, we will mark it as capital L, is equal to 0.35 meters. So now let us go into some basic analysis, some equations, and then we will continue this experiment with different conditions. So we mentioned previously that the condition for diffraction maximum, for diffraction grating, is the following: d times sinus theta is equal to m times lambda. We will consider first order diffraction maxima. That's why we can write that lambda is equal to d times sinus theta. This is the condition of our first order diffraction. So if we look on this, our experimental setup from top, so this is a CD disk, and we consider only already diffracted light. So here is beam which forms the central or zero order diffraction maximum, and these two beams are corresponding for first order diffraction maximum. So here is angle theta. This is the distance x between the zero and first order diffraction maximum, and this distance is capital L, the distance between the CD disk and our screen. So taking this into account, sinus theta can be expressed as x divided by square root of L square plus x square. So now taking this into account, we can write that lambda, the wavelengths, are known parameter which we want to determine will be equal to d period of the diffraction grating. We know that is the given information from manufacturers of CD and DVD discs times x, distance between the 0 and first order diffraction maxima, divided by square root of L square plus x squared. So this is how we are going to analyze our experimental data in order to get the wavelengths, unknown wavelengths of incident light, a monochromatic light. So let us move to another experiment. Here we have the same CD disc placed at the same distance. So here we have capital L equal 0.35 meter, but we change the light source. So now we use blue laser, and we actually see now even more complex picture. So we see the zero order, we see first order diffraction and second order diffraction maximum. So that happens because the wavelength of blue light is shorter than red, so the distances between the corresponding diffraction maximum shrinks. So now we do the same procedure, so we can measure the distance between two neighboring diffraction first order diffraction maxima divided by 2, we get the distance between 0 and first diffraction maxima will be x equal to over 2, and in this case we get smaller, obviously, distance this in comparison to red light, so this is 0.095 meter. So what we can do next, we keep in mind these parameters. We will later write them down separately for all our experiments, just for demonstration purpose. We kind of highlight them here on the images of the diffraction patterns. So next, what we can do, we can repeat the same experiment with blue laser, but in this case we will change the diffraction grating from CD to DVD disc. So now we have already DVD disc. It is placed at the same distance. Capital L is equal to 0.35 meter. And what we see here, that wavelength now is the same as on the previous slide. However, the distance is much larger between diffraction, first order diffraction maximum, and we already don't see in the scope of like the scale of our experiment, we don't see in the second order diffraction maximum because they're like too far, go beyond the our improvised screen. So here in this case, distance between 0 and first order diffraction maximum x will be equal to L over 2, and that is equal to 0.225 meter. Meter. So what do we have now? We have CD diffraction grating, two different wavelengths, red and blue, LEDs, and also we have blue LED, diffraction, blue laser, light diffraction on DVD diffraction grating. We do not perform here diffraction of red light on DVD diffraction grating because the distance between the two neighboring, like this, two first order diffraction maxima becomes so large that it doesn't fit on our screen, and we don't want to move this setup, so don't want to change the distance from the disk to the screen. So we keep this constant. So now let us go to the next slide and summarize our experimental data. So we have, let's say here will be L, distance from the disk to the screen. Here will be X, and here will be diffraction grating period. So distance is 0.35 meter for our first experiment. Then we have X, distance between 0 and first order diffraction maximum for red light, 0.16 meter. Period of diffraction grating is 1.6 10 to minus 6 meter, and we know that this is CD diffracting grating. Then second experiment was the same distance between the diffracting grating and screen. Then we had blue light, so we can write here like this is red, this is blue. Distance was 0.095 meter, and the same diffracting grating period, 1.6 10 to minus 6 meter. This is also CD diffracting grating. And again we have blue laser. Distance stays the same between diffracting grating and the screen, and we get distance between 0 and first diffraction maximum, 0.225 meter, with the period of diffraction grating 7.4 10 to minus 7 meter, and this is DVD diffracting grating. So now we have our experimental results. If we use this equation, which we derived previously for determining the unknown wavelengths for red and blue light, we get, so this equation D is diffraction period, the period of diffraction grating, times X times L in second power plus X in second power. So this is our equation. By applying to this experimental data, we get the expression for wavelengths lambda. So for red light, we will get 6.65 10 to minus 7 meter, or this will be equal to 665 nanometers. Then for blue uh, laser, wavelengths determined with CD diffracting rating will be 400, like 4.19, 10 to minus 7 meter. That is 419 nanometers. And the same light source, the same blue laser, but wavelengths determined with DVD diffraction rating was 4.0, 10 to minus 7 meter, and that is 400 nanometers. So we have some discrepancy here, but they still are quite close to each other. And we see that there is a big difference between the wavelengths of the red laser and blue laser. So if we consider here some average, that will be around 410 nanometers. So we get, let's say, 665 nanometers and some average value for, so that for red uh, laser, and some average value of the wavelengths 410 nanometers for blue laser. So let's write here red wavelength is equal to 665 nanometers, and blue wavelength is some average 410 nanometers. So this is our finding based on very simple and demonstrational experiment utilizing just CD and DVD discs as diffracting grating and a regular ruler with very simple experimental setup. So now it would be good to double check with some um, specifically designed instrument how well we determine the wavelengths of these red and blue lasers with our simple experimental setup. So for that purpose, I used in our like experimental lab focused on optoelectronic and photovoltaic devices, uh, specialized equipment, the so-called spectrophotometer. So if we shine some laser beam inside this optical fiber, it goes eventually into the spectrophotometer, and it is, we have here embedded system with commercial diffracting grating or prism, optical prism, which splits the incident light in the spectrum. And then we have calibrated linear CCD detector, which will directly provide information to the software installed in the PC about the spectral distribution of incident light. So since we are dealing here with monochromatic light, so we should see some sharp peak at some wavelengths which corresponds to the wavelengths of the um, incident light. So this is the experimental setup, how it looks. So it's arranged quite simple. We just shine LED laser beam in this optical fiber, and we immediately get the spectral distribution of incident light on the PC. So that's how it looks. So this is the spectral distribution for our red LED laser. We see a very sharp peak at position at 660 nanometers. So this is the true wavelength of this laser. And if we compare this with the blue LED, we get the sharp peak position at 407 nanometers. So as you remember, let's come back to previous slide. We got from our simple and demonstrational experiment that wavelength was 665 nanometers, quite close to the real value. Also, if we consider for blue LED, our average wavelength determined from two experiments with different diffracting gratings, CD and DVD, was 410 nanometers, which is also quite close to the real wavelength of this laser, 407 nanometers. So we not only demonstrated the application of diffraction gratings for generalized purpose of determining unknown wavelengths, but also our actual experimental findings reveal that such a simple system based on CD or DVD diffracting grating with very demonstrational experimental setup, let's say demonstrational level experimental setup, provides us with quite decent accuracy. Moreover, if we perform these experiments multiple times and get average with standard deviations, then of course our confidence in the final result can improve significantly, and we can really come to the actual values for the wavelengths of incident light, which is emitted by lasers or any other sources of light which are available to us and are of our interest. That why it could be even used in some introductory level research projects where we indeed will determine wavelengths of incident light or spectral distribution of incident light using such simple diffracting gratings as CD and DVD disks. So as final step, we used specialized scientific equipment, spectrophotometer, in order to determine the actual wavelengths of the light emitted by red and blue LEDs, and we got values 660 and 600 and 407 nanometers for red and blue LEDs respectively, which are quite close to our determined values, 665 for red nanometers for red LED and average 410 nanometers for blue LED. I hope that this experiment was interesting for you guys as a demonstration for diffraction grating application. Thank you very much for your attention. Have a good evening. Bye bye.